Hello, this is Mohammad Al Olaimat, and my supervisor is Dr. Serdar Bozdag from the University of North Texas. Today I'm presenting my research project titled Predicting Alzheimer's Disease Progression Using a Bidirectional Gated Recurrent Unit-based Architecture. Alzheimer's disease is a neurodegenerative, irreversible disease that affects millions of people worldwide. According to Alzheimer's disease, people can be classified into three states: cognitive normal, or Alzheimer's disease, or mild cognitive impairment, which is an intermediate stage between normal and Alzheimer's state. The main problem of the diagnosis of Alzheimer's disease is that the diagnosis is made after the appearance of significant symptoms of dementia, such as short-term memory loss and others. To analyze the progression of Alzheimer's disease, patient data is kept in electronic health record, which is sequential data. Recently, recurrent neural networks have been successfully used to handle these electronic health records. There are three problems that have motivated us in this project. Diagnosis of Alzheimer's disease at the onset of disease brings a huge burden on patients and their caretakers and the healthcare sector as well. Thus, there is a crucial need to develop a method for early prediction Alzheimer's disease for people who are at the intermediate stage. Second, as mentioned earlier, patients' data is kept in electronic health record. However, these records have a common problem, which is a regular time interval between successive visits. Unfortunately, recurrent neural network ignores this problem while it analyzes such data. So there is a need to address this problem. To address previous problem, our contribution were as following. For early prediction of conversion of Alzheimer's disease, we have designed two bidirectional gated recurrent unit-based deep learning models. The first one to predict conversion of Alzheimer's disease at next visit only, while the second method to predict conversion of Alzheimer's disease at multiple visits ahead. The second contribution was using age of patients in each visit to minimize the effect of irregular time interval problem between visits. Finally, to maximize our model robustness, we have used a customized loss function to increase the model sensitivity by giving more weight to predicting conversion to Alzheimer's disease. To describe our model, I will explain only one architecture, which is predicting the conversion of Alzheimer's disease at multiple visits ahead. The architecture composes of three parts: encoder part, decoder part, and multi-layer perceptron part. In encoder part, two gated recurrent units in both directions are used to gain the latent representation from longitudinal data using this formula. After we got the latent representation is going to be used by the decoder part to generate multiple visits ahead, and let's say n visits. Then the last visit is going to be concatenated with the demographic data to feed the multi-layer perceptron to predict the diagnosis at that visits using this formula. To give more weight on predicting conversion to Alzheimer's disease cases, all parameters for both bidirectional GRU and multi-layer perceptron are updated in an integral way using a modified binary cross entropy as a loss function. This is the loss function. In this equation, alpha is a hyperparameter between 0 and 1 that defines the relative weight of positive prediction. In our case, we set alpha to 0.7. Y represent the true diagnosis and Y prime represent the predicted diagnosis. To evaluate our model, Alzheimer's disease neuroimaging initiative dataset has been used. The dataset is a cross-sectional and longitudinal data from three different data modality, which are demographic, cognitive performance, and magnetic resonance imaging data. We compared our model to a gated recurrent unit and long short-term memory. For comparison, we have trained for each model 4 models using 2 visits or 4 visits or 7 visits or 10 visits to predict the next 4 ahead visits. X-axis represent the scenario, while the Y-axis represent the F2 score. As can be seen in from the figure, our model outperformed all baseline model for all cases in 14 out of 16 cases. To conclude this presentation, we have designed a 2 bidirectional GRU based architecture to predict the progression of Alzheimer's disease at next visits and future visits. The results showed that our proposed model outperformed baseline models in terms of F2 and area under the curve. Finally, I would like to thank my supervisor, Dr. Serdar Bozdag, and all my colleagues in Dr. Bozdag lab. This project was supported by NIH. Finally, here is some information about my poster. Thank you for listening.